Sega.
Okay, in this video we're going to look at hexadecimal, and hexadecimal is a number system. We've covered base 2 and base 10. Hexadecimal is base 16, which means it uses 16 values. But first of all, let's figure out why we use hexadecimal. And to do that, we need to understand the problem with binary. Now, binary is great for computers because computers understand two states, and binary gives you two states. A 1 is one state and a 0 is another state. But the problem is binary numbers grow massively, and that's difficult for humans to work with. Fine for computers to work with, difficult for humans to work with. So in order to shorten down a binary number, we use hexadecimal notation because it allows us to represent long binary numbers in short form. So hexadecimal has a great relationship with binary because if you can split a binary number up into nibbles, for example here, it correlates nicely to the hexadecimal value. For example, a nibble of 1s actually represents 15, so we can represent it as an F. A nibble of 12 can be represented as a C. So I'm going to try and show you a simple example of how to actually split a binary number up and represent it as hexadecimal. So there's three stages. There's step 1, which is split the number into nibbles. So I've got an 8-bit number here. I need to split that up into nibbles. I'm going to show you how to do that in a second. The next thing I need to do is calculate the nibble into a denary value, which is also very simple. And then the last thing we need to do is turn the denary number into a hexadecimal character. So let's have a quick look at how we do this. The first thing I'm going to do is I'm going to split this long number up into, I'll use a different coloured pen just to make it easier. I'm going to split this up into nibbles. So I'm going to take the first 4 and just draw a line through. So right now I've got a nibble. Now if we take this nibble, if we say that this is the 8, this is a 4, this is a 2, that's a 1, what we've got here is the value 9 as a nibble. And if we have a look here, we've got 1001, okay, which is 9 there. So this in hexadecimal would be 99. Now that doesn't seem too difficult to do, and you're probably thinking, well, it's not really, because what this value really is 128 plus 16 plus 8 plus 1, which is a completely different value. But what we're doing there is we're looking at it in base 10. Let's have a look at a more difficult example. Again, I'm going to split this up here. Now again, I go into 4s. So there's the first split. There's the first split. So now the next step is to convert these nibbles into denary. So we have 0, 1, 1, 0. So that is a 4 and a 2. So this is a 6. 4 1s is a 15. And then this is a 9 again. So we've got the value 9, 5, 6. Now, what we've got to remember is that 10 equals an A, all the way up to 15 equaling an F. So therefore, this hexadecimal number is really 9. We don't use the 15 because there is no 15 numeral in hexadecimal. We use F. 9, F. 6 is the equivalent to 1001, 1111, 0110. Can you see how hexadecimal allows you to shorten this 12-digit binary number into 3 digits like these? I'll just show you another example shortly. So here are 3 more examples which I'll try and work through. If you want to have a go at these cells and pause the video, go ahead, but the first one we're going to try is this one, the first one here, and I'll just split the nibbles up. So here we go, there's the first nibble, there's the second nibble. Now the first nibble is an 8 and a 4 and a 0, 0, so the first one's a 12, we'll just put the 12 there. Then we have a 4 and a 2 and a 1, which is a 7, so we'll put the 7 there. And if we have the 1, 0, 1, 1, which is an 8, a 2 and a 1, we've got 11. So if we have a look at this carefully, remember A equals a 10, and we have B which equals an 11. So this value here we need to get rid of, and we'll have the value b. We keep the number 7, and then we've also got the value 12, so c is 12 in hexadecimal. So the first number here is B7C in hexadecimal. We'll just have a quick look at the second example. Let me just take this out. We'll leave that here for reference, and I'll just put in the D and the E and the F. So we've got D, E, and F, which equal 13, 14, and 15. So again, 3 steps. Split them up into nibbles, and this 4 ones is a 15, and then we've got a 0 and a 15, and we know 15 is an F, so this number here is F, 0, F. And finally, what do we do when we've got a number of digits that you can't split into 4? So we've got a 4 here, and we've got a 4 here. What we do is we leave these 2 digits here, and we'll pretend that there's 2 zeros on the end. Okay, always. It's always got to be 2 zeros on this left-hand side. Nowhere else on the left-hand side, that's where the 2 zeros are. So if this is the case, we have a 3, a 3, and a 3. So the hexadecimal value for 0011, 0011, 0011 is 333. Now this doesn't give you an example of how hexadecimal actually works. It just shows you how to answer questions which might appear on the exam paper.